Good morning, students. Now I am going to discuss about the thermodynamic potentials. To study the thermodynamic potentials, we should know first law of thermodynamics and second law of thermodynamics and a few mathematical preliminaries. So first law of thermodynamics I have already explained in my previous video. Second law of thermodynamics, it is related to the entropy. Entropy is a measure of the disorder of the system. So consider an infinitesimal process in which a system changes from one equilibrium state to another equilibrium state. You know what is an infinitesimal process? It is a very small process that happens in the system. So entropy in such a system can be defined as the ratio of infinitesimal amount of heat transferred during a reversible process to the absolute temperature. So ds, that is change in entropy, is equal to dq by T, where dq is the infinitesimal amount of heat transferred during a reversible process and T is the absolute temperature. The mathematical preliminaries. Theorem 1. If z is a function of two independent variables x and y, so z can be expressed as z is equal to z of x comma y. Then according to calculus, dz is equal to dou z by dou x at y into dx plus dou z by dou y at x into dy, where dz is an exact differential. Only if it is exact differential, according to calculus, we can write this equation. Okay, this also I have explained in the previous video. Now let capital M is equal to dou z by dou x at y and n is equal to dou z by dou y at x. Substitute equation 2 in equation 1. So in the place of dou z by dou x at y, substitute m, and dou z by dou y at x, substitute n. After substituting, you will get dz is equal to m into dx plus n into dy. Now the second mixed partial derivatives. What do you mean by second mixed partial derivatives? Second is dou square. Okay, and mix it, you will have both dou x and dou y. Partial derivatives we will write in terms of dou, right? So the second mixed partial derivatives are dou square z by dou y dou x is equal to dou square z by dou x dou y. So this dou square z I can write as dou into dou z, and this I am going to split this dou y and dou x. So dou by dou y into dou z by dou x is equal to dou by dou x into dou z by dou y. But what is dou z by dou x? It is capital M. If you see equation 2, dou z by dou x is capital M and dou z by dou y is capital N. So you can substitute that. We will get dou into, so dou by dou y of dou z by dou x is capital M. So we got dou m by dou y at x is equal to dou n by dou x at y. This is known as the condition for exact differential or perfect differential. Next, theorem 2. If a quantity f is a function of x, y and z and relation exists among x, y and z, then f can be regarded as a function of any two of x, y and z. Okay, so f of either x comma y or f of y comma z or f of x comma z. So f can be regarded as a function of any two of x, y and z. Similarly, any one of x, y and z can be considered as a function of f and any other of x, y and z. That is, x is equal to x into f of x of f comma y. See, any one of x, y and z. Let us take x. So x is equal to x of, it is considered as a function of f and any other of x, y and z. So f comma y. Similarly, you can take y is equal to y of f comma z. Fine. So now let us take x be a function of f and y. That is, x is equal to x of f comma y. Now you apply the exact differential. Dx is equal to dou x by dou f at y into df plus dou x by dou y at f into dy. Similarly, let y be the function of f and z. That is, y is equal to y of f comma z. So dy is equal to dou y by dou f at z into df plus dou y by dou z at f into dz. Substitute equation 4 in equation 3. That is, instead of this dy in equation 3, substitute this RHS in equation 3. RHS of equation 4 in equation 3 in the place of dy. So substituting, what will we get? Dx is equal to dou x by dou f at y into df plus dou x by dou y at f into, instead of dy we will write dou y by dou f at z into df plus dou y by dou z at f into dz. So that is what is written here. And now with this term, so the first term remains the same. With the second term, multiply each term inside the bracket. So you will get dou x by dou y at f into dou y by dou f at z into df plus dou x by dou y at f into dou y by dou z at f into dz. Now you group the df terms. So the first and the second term have df. So take df outside. Dou x by dou f at y plus dou x by dou y at f into dou y by dou f at z plus the third term you write like the same. There is no change in the third term. That is taken as equation 5. Now let us take x as a function of f and z. That is, x is equal to x of f comma z. So dx is equal to dou x by dou f at z into df plus dou x by dou z at f into dz. Now equate the dz terms in equation 5 and equation 6. Okay, only the dz term you can equate. So what will we get? Equating, we get dou z by dou x at f is equal to dou x by dou y at f into dou y by dou z at f. Okay, so we are equating only dz terms. After equating, now bring everything towards one side. So dou x by dou y at f, dou y by dou z at f, and the term on the LHS, bring it to the RHS. So in the LHS you have dou x by dou z. When it comes to the RHS, it will become dou z by dou x at f. Now if you see, I can cancel all the terms. Dou x, dou y, dou y, dou z, dou z. So finally I am getting 1. This is theorem 2. So with these understandings, or with this knowledge, we can study the thermodynamic potentials. Thermodynamic potential is a quantity used to represent the state of a system. Okay, it is a quantity used to represent the state of a system. They are the potential energy. Okay, they are the potential energy defined as capacity to do work. There are 4 thermodynamic potentials. They are internal energy U, enthalpy H, Helmholtz free energy F, Gibbs free energy G. So we shall see one by one. First is internal energy. Internal energy is the total energy of the system, which is not subject to the action of external force. That is the total energy of the system when the system is not subjected to the external force. Now, according to first and second law of thermodynamics, we know the first law, it is dq is equal to dw plus du. Rearranging, we get du is equal to dq minus dw. Because our heading is internal energy, so we have to write in terms of internal energy U. Okay, the symbol for internal energy is U. And Q is heat, W is work done. But according to second law of thermodynamics, dq is equal to TdS. Fine, dq is equal to TdS. So du is equal to TdS minus PdV, because work done can be written as P into dV. So we got du is equal to TdS minus PdV. This equation gives the change in the internal energy of the system in terms of 4 thermodynamic variables: pressure, volume, temperature and entropy. Yes. Okay. S is what? Entropy. Entropy is the disorder of the system. And this is called the first thermodynamic potential. So, internal energy is the first thermodynamic potential. Now, if a pure substance undergoes an infinitesimal change, okay, that is, if it undergoes a small change, equation 1 becomes, see equation 1, it is du is equal to TdS minus PdV, right? So at constant volume, fine, at constant volume, what happens to this PdV? It becomes 0, right? Constant volume means volume remains constant, that is V is equal to 0. If V is equal to 0, then PdV is equal to 0. So you will have only these two terms, du is equal to TdS. So for infinitesimal change, the derivatives become partial. So instead of du, we have to write dou u. So dou u by dou s. Okay, this ds, when it comes to the denominator, okay, so we can write it as du by ds. And since the derivatives are partial, we will write dou u by dou s. At constant volume is equal to T. See, I have written dou u by dou s at constant volume is equal to T. Similarly, dou u by dou v at constant s is equal to minus P. You can see here, at constant s, this term will become 0. So you will have du is equal to minus PdV. So at constant s, the derivatives become partial. So you will have dou u by dou v at constant s is equal to minus P. Okay, dou u by dou v at constant s is equal to minus P. Now for an adiabatic process, heat remains constant. Therefore equation 1 becomes dq is equal to 0. So if you see here, dq is equal to 0, therefore du is equal to minus dw or minus pdv. Okay, du is equal to minus pdv. This shows that the work done by the system in an adiabatic process is equal to the decrease in the internal energy of the system. Okay, work done is P into dV. So work done by the system in an adiabatic process is equal to the decrease in the internal energy of the system. You have minus over here. Fine, so it is decrease. Now for an isochoric adiabatic process, what happens? Volume and heat remains constant. Therefore equation 1 becomes, see this is equation 1, so volume constant and heat constant, that is Q term becomes constant. Therefore we will have du is equal to 0. Okay, so dV is equal to 0 and dq is equal to 0. Therefore du is equal to 0. This implies u is a constant. Thus the internal energy of a system remains constant in an isochoric adiabatic process. Hope you all understood. Same way we have to write for enthalpy. So what is enthalpy? Enthalpy is defined as the total heat of the system. Okay, it is defined as the total heat of the system. It is given by H is equal to U plus PV. As U, P and V are state variables, H is also a state variable. Okay, and enthalpy has a dimension of energy, but it is not a specific form of energy. In the beginning I said thermodynamic potentials, they are similar to potential energy. So enthalpy has the dimension of energy, but it is not a specific form of energy. Now if the system undergoes infinitesimal change, then dH is equal to, do the differentiation of this equation. So dH is equal to du plus pdv plus vdp. What is du plus pdv? From first law of thermodynamics, it is dq. So instead of this, substitute dq plus vdp. Next, what is dq? It is TdS from second law of thermodynamics. dq is equal to TdS. So I have substituted that. So this is equation 2. That is dH is equal to TdS plus vdp. Now divide both the sides of equation 2 by dt. So we will get dH by dt is equal to T into ds by dt plus v into dp by dt. At constant p, the derivatives become partial. Then equation 3 becomes, so in this equation at constant p, this term, that is the second term, becomes 0. That is v into dp by dt becomes 0. So we will have only these two terms, that is dH by dt and t into ds by dt. So at a constant p, the derivatives become partial. So we are going to write as dou h by dou t at p is equal to t into dou s by dou t at p. This is nothing but, what is t into dou s? It is dou q. So dou q by dou t at p. This is nothing but Cp, where Cp is the specific heat capacity for 1 mole of a gas at constant pressure. And Cp is given by dou q by dou t at p. Now, if a pure substance undergoes an infinitesimal change, equation 2 becomes, okay, equation 2 is this, dH is equal to TdS plus VdP. So if the pure substance undergoes infinitesimal change, then at a constant P, this VdP will become 0. So we will get dou H by dou S at constant P is equal to T. You can see here. So dou H by dou P at a constant S. Where is that equation? Dou H by dou P at a constant S is equal to V. Similarly, dou H by dou S at constant P is equal to T. Fine. Hope you understood how to write this. So we have to make the derivatives constant. So in this we have entropy ds and dP. So we will consider when the pressure is constant. So the second term will become 0. We will have only dH is equal to T into ds. So at constant P, this becomes dou H divided by dou S is equal to T. Okay, so dou H by dou S at constant P is equal to T. Similarly, dou H by dou P at a constant S is equal to V. Now for reversible isobaric process, pressure remains constant. Then equation 2 becomes, okay, this is equation 2. When pressure remains constant, we have dH is equal to TdS. So therefore dH is equal to TdS. TdS is nothing but dQ. Thus for an isobaric process, enthalpy, the change in enthalpy is equal to the heat absorbed, because we got dH is equal to dQ. So change in enthalpy is equal to the heat absorbed. Now for an adiabatic isobaric process, heat and pressure remains constant. So equation 2 becomes, in equation 2 dP term will be 0 and dQ term will be 0. Therefore dH term is equal to 0. I will show equation 2. So for adiabatic isobaric process, for adiabatic process, dQ term will be 0 because heat remains constant in adiabatic process, and for isobaric process dP becomes 0. Therefore dH is equal to 0. Thus for an adiabatic isobaric process, enthalpy is a constant. Okay, since dH is equal to 0, this implies H is equal to constant. Thus enthalpy is a constant for an adiabatic isobaric process. Next is Helmholtz free energy. Helmholtz free energy is defined as F is equal to U minus Ts. As U, T and S are state variables, F is also a state variable. Helmholtz free energy has the dimension of energy, but it is not a specific form of energy. Okay, same thing like enthalpy, we have to write as U, T and S are state variables, F is also a state variable. Helmholtz free energy has the dimension of energy, but it is not a specific form of energy. And if the system undergoes an infinitesimal change, then dF is equal to du minus TdS. So here you have to do the differentiation for infinitesimal change. df is equal to du minus t into ds minus s into dt. That is what it is written here. Next, what is du? According to first law of thermodynamics, du is equal to dq minus pdv. So I have written dq minus pdv. Now this minus tds minus sdt. And what is dq according to second law of thermodynamics? It is tds. So tds minus pdv minus tds minus sdt. Here plus tds minus tds, it becomes 0. Therefore df is equal to minus pdv minus sdt. This is equation 4. Now for an infinitesimal change, the derivatives become partial. Therefore equation 4 becomes, see here, at constant temperature dt terms become 0. So we will have df is equal to minus p into dv. So I can write at constant temperature the derivatives become partial. So dou f by dou v at constant t is equal to minus p, and dou f by dou t at constant v is equal to minus s. So at constant v, this term, the first term in the RHS becomes 0. We will have only df is equal to minus sdt. So when for the infinitesimal change, dou f by dou t at constant v is equal to minus s. Now for a reversible isothermal process, temperature remains constant, because isothermal is a process where temperature remains constant. Therefore equation 4 becomes, dt becomes 0, therefore we will have df is equal to minus pdv. What is pdv? It is the work done. So the work done in a reversible isothermal process is equal to the decrease in the Helmholtz free energy. There is a minus sign, so it is a decrease in the Helmholtz free energy. Now for an isothermal isochoric process, temperature and volume remains constant. So if you see equation 4, for isochoric process the first term becomes 0, for isothermal process the second term becomes 0. Therefore df is equal to 0. This implies f is a constant. Thus Helmholtz free energy remains constant in an isothermal isochoric process. Next is Gibbs free energy. Gibbs free energy is defined as G is equal to H minus Ts. Once again, as H, T and S are state variables, G is also a state variable. And Gibbs free energy has dimension of energy, but it is not a specific form of energy. Equation 5 can be written as G is equal to U plus PV minus Ts, because H is equal to U plus PV. So substitute that in equation 5, so you will get U plus PV minus Ts. Now if the system undergoes infinitesimal change, then equation 6 becomes dg is equal to du plus p into dv plus v into dp minus t into ds minus s into dt. Now what is du plus p dv? From first law of thermodynamics, it is dq. So dq plus v dp minus tds minus sdt. Now what is dq from second law of thermodynamics? It is tds. So dg is equal to tds plus vdp minus tds minus sdt. Here plus tds minus tds will become 0. Therefore dg is equal to vdp minus sdt. Okay. Now for an infinitesimal change, the derivatives become partial. Therefore equation 7 becomes, as usual, you keep the derivatives as constant. So first you keep t as constant. When t is constant, the second term becomes 0. So you will have dou g by dou p at a constant t is equal to v. Similarly, at a constant p, the first term will become 0. So you will have dou g by dou t at a constant p is equal to minus s. Okay. Now for an isothermal isobaric process, temperature and pressure remains constant. Therefore equation 7 becomes, see, temperature remains constant, so the second term becomes 0. If the pressure remains constant, the first term becomes 0. Therefore equation 7 becomes dt equal to 0 and dp equal to 0. Therefore dg is equal to 0. This implies g is a constant. Thus Gibbs free energy remains constant in an isothermal isobaric process. Now significance of thermodynamic potentials. A mechanical system is in stable equilibrium when the potential energy of the system is a minimum. Okay, a mechanical system is in stable equilibrium when the potential energy of the system is a minimum. Okay, you can strike out this is not there. So when the potential energy of the system is minimum, when the mechanical system is in stable equilibrium. So the behavior of internal energy, enthalpy, Helmholtz free energy and Gibbs free energy is similar to the potential energy. So when these are minimum, when internal energy is minimum, that is, internal energy of a system remains constant in an isochoric adiabatic process. Just now I have explained all those. And enthalpy is a constant for an adiabatic isobaric process. Helmholtz free energy remains constant in an isothermal isochoric process, and Gibbs free energy remains constant in an isothermal isobaric process. These are the significance of thermodynamic potentials. Next, Maxwell's thermodynamic relations using thermodynamic potentials. So the properties of a pure substance is represented in terms of 4 thermodynamic potentials. They are internal energy U, enthalpy H is equal to U plus PV, Helmholtz free energy F is equal to U minus Ts, Gibbs free energy G is equal to H minus Ts. Now for a hydrostatic system undergoing an infinitesimal reversible process from one equilibrium state to another, the internal energy changes by an amount du is equal to Tds minus Pdv. These equations we saw while explaining internal energy. Okay, so U, T and P are imagined to be functions of S and V. Similarly for enthalpy changes by an amount dH is equal to du plus Pdv plus Vdp, because H is equal to U plus Pv. So for infinitesimal change, dH is equal to du plus Pdv plus Vdp. But du plus Pdv is nothing but dq and dq is nothing but Tds. So Tds plus Vdp, where H, T and V are imagined to be functions of S and P. Next, Helmholtz free energy changes by an amount dF is equal to du minus Tds minus STT. So you can refer the previous steps. You can go to Helmholtz free energy and you can check it out. your final equation is minus PdV minus SdT. Here again this F, P and S are imagined to be functions of T and V. Next, Gibbs free energy, it changes by an amount dH is equal to dG is equal to dH minus TdS minus SdT, that is equal to VdP minus SdT. For this also you can go to Gibbs free energy and you can check it out for the equations, where G, S and V are imagined to be functions of T and P. Since U, H, F and G are state variables, their differentials are exact differentials of the type dz is equal to m into dx plus n into dy. We saw in the theorem dz is equal to m into dx plus n into dy, where z, m and n are the functions of x and y. Therefore, we can write dou m by dou y at x is equal to dou n by dou x at y. Okay. Now applying these results to the four exact differentials du, dh, df and dg, we get, see, these are the equations, that is du is equal to tds minus pdv, hence we get dou t by dou v at S is equal to minus dou p by dou s at v. If you consider here dz is equal to m into dx plus n into dy. So dou m by dou y, dou m by dou y at x is equal to dou n by dou x at y. Fine. So the same way you have to write. So in the place of m we have t, okay, m into dx plus n into dy. So dou t by dou v at s is equal to minus dou p by dou s at v. Same way you have to write for enthalpy, Helmholtz free energy and Gibbs free energy. So enthalpy dH is equal to TdS plus VdP. So we can write dou T by dou P at S is equal to dou V by dou S at P. Similarly, dF is equal to minus SdT minus PdV. Hence, dou S, see, you will have minus sign both the sides. So, minus minus will get cancelled. So, dou S by dou V at T is equal to dou P by dou T at V. And the fourth equation, dou S by dou P at T is equal to minus dou V by dou T at P. So these are these four equations on the right, that is 1, 2, 3, 4. These four equations are known as Maxwell's equation. Hope you all understood the thermodynamic potentials and how we derived Maxwell's equation from thermodynamic potentials. Thank you.